In order for us to take that notion of conditional independence forward, there is a lot more interesting things you can do. You can create what is known as Bayesian networks. Bayesian networks are basically representing a probability distribution graphically in terms of what are the effects, what are the different possible causes which can lead to the effort. Then arcs actually depend and tell you that there is a conditional dependence between one observation and potential causes. Example, as we saw, wet garden, we said only two, not rain, but you could fine grain it. You could say, is it rain? Is it because of tap? Then after wet rain, you could say slip, but at slip itself, you could have multiple causes, right? It could be because of wet garden, or it could be because you have a cramp in the leg. So if you take any generic real life scenario, this Bayesian network offers a very naive way, very intuitive way of capturing cause-effect relationships and is a very powerful machine learning tool for explaining several scenarios. So what is the advantage we get by representing, a thing like a set of information like that? The beauty which Bayesian networks carry, exactly like what we said in the previous case of being able to independently multiply probabilities of each variable and combining that to get you the combined instance probability. Here we have similar kind of independence. Say that you assume you created a Bayesian network. We basically have a very simple theorem here which says that a node is conditionally independent of its non-descendants given its parents. Means if you have a tree somewhere in the third level node, you only have to worry about the conditional probability of it with respect to its parent. Anything above that, normally what you would expect is you will try to carry, if you have a V1, V2, Vn, etc., you would say V1 given some previous parents, so that instance happened, then the previous instance, parents instance happened, etc. But you can simplify that now saying that you only have to worry about immediate conditional independency, conditional probability of the child given the parent. So, example I was giving you how this is useful in several interesting cases is like let's take an example of diagnosis of some fault which has happened in your car. This is a classical Bayesian network diagram. You start with, is there a crank? Then you start saying that, okay, there's a problem with compression, spark plug you do, or tailpipe smell. Then you go and look at what it can lead to. It can either lead to no fuel. So you see that at the bottommost layer, you have the final symptoms, and then you go back and see the causes going backward, upward from there. So you can observe no fuel, or you can observe something like no spark. Then you go work backwards. It could be because spark plug, you can do the test, or you can do the test related to aerosol starting. So the idea is that such a diagnostic network gives you the knowledge of what is the cause-effect relationship of faults which happen in a car. What are the root causes? This is the same thing we can do in a healthcare scenario. In fact, if you see today IBM Watson, when they're being using in healthcare, this is what they're building. They're building large Bayesian kind of networks which are giving a tree of cause effect from disease to symptom kind of scenarios. Why is it useful? As I said, it's useful in diagnosis of potential cause when you see a set of symptoms. So why is it possible to create a Bayesian network from a simple Bayesian classifier? It is possible because of this notion of conditional independence of a node on only its immediate past parent, then carrying around node for all the conditional probability with respect to all the predecessors. So that gives you a very simple formula for calculating the probability at a node, which is basically multiplying with the immediate parent conditional probabilities. So Bayesian networks are generalizations of Bayesian classifiers useful for representing